Hello everyone, my name is Saurav Gupta. I am working as a research engineer in Mercedes-Benz Research India. This work is in collaboration with my colleagues Saurav, Abhay and Rahul. This talk will describe our work on how vision transformer networks can be used effectively in weakly supervised object localization. In WSOL, the goal is to leverage weak supervision to know the location of the object. In this setup, we are constrained to achieve this without any bounding box annotation, thus saving a lot of annotation cost. Below, we show generated localization map for wolf and bird respectively. In WSOL, we need to understand which weak labels to use. In our case, we use object class labels as weak supervision. Next, we choose a network architecture and train for classification tasks using our chosen weak labels. Finally, we need a map generation mechanism using which we can aggregate learned features from different layers of the trained network. It is very important to train a model in a way that we get rich features which covers the entire object. We identify some common problems that exist in WSOL. Generally, classification models have tendency to only look at discriminative features as they are not directly trained to perform localization. For example, in case of dog, only eyes are highlighted. Also, localization maps are not class specific. For example, the map activates multiple regions across the image apart from volleyball. Third problem is that due to cluttery environment and background noise, localization maps are not very precise. We try to address these problems using our method ViTOL as you can see in the third column. Here we list some key contributions of our method. We choose Vision Transformer to train a classification network due to its self-attention mechanism and better capability to learn long-range interactions. Next, we introduce an architectural change to Vision Transformer. We add patch-based attention dropout layer called p-ADL layer, which aids the model to discover non-discriminative regions for better localization. We also introduce gradient attention rollout named GAR, a novel map generation mechanism which gets rid of negative contributions and introduces class dependency. Combining above key contributions, we achieve state-of-the-art results on ImageNet and CUB datasets. We compare our method with the baseline approach where we take standard vision transformer and perform classification. It tokenizes the image in the form of patches and learn interactions between them. In ViTOL, we make an architectural change by adding p-ADL layer in each encoder block as seen in the diagram. Motivated from ADL layer in CNNs, we design a p-ADL layer which processes the output from each MLP layer. This layer comprises of two main components, patch drop mask and patch importance map. Patch drop mask drops the highlighted region based on a drop threshold. Patch importance map highlights the activated region using sigmoid operation. One of these components is selected randomly during training time based on an embedding drop rate alpha. When patch drop mask is selected, the network is forced to look at remaining portions of the object to classify it correctly. As seen in the crane example, each block progressively discovers other parts of the object as the earlier layers have dropped the highlighted ones. This scattered information in different layers of the train network is then aggregated through our map generation method called GA. Here we showcase the effect of using p-ADL on generated localization map. In case of training without p-ADL layer, entire objects are not discovered, whereas with p-ADL layer, entire region for barbell and leopard are localized. In ViTOL, we improve the attention rollout mechanism by introducing a gradient term and we name it gradient attention rollout GAR. Here, first two equations directly come from attention mechanism in transformer. We compute the gradients corresponding to softmax attention metrics and take a dot product. We perform first three steps for each layer and recursively multiply to get the final localization map. We also compare our method against another map generation method called layer relevance propagation LRP. We showcase some examples how introducing gradient maps helps in achieving class dependency. We can clearly see that in case of tie-in basketball, our method does better in generating class-specific localization map as compared to attention rollout, which highlights the person as well. We compare against other state-of-the-art methods in WSOL on ImageNet dataset. We achieve best scores in all the metrics. Here we compute maxbox accuracy V2, which is a better measure of localization for both datasets. We achieve a large boost over previous methods. We also compare qualitatively on ImageNet dataset with other SOTA methods such as CAM, ADL, TSCAM. Our method not only highlights the object boundaries precisely, but also highlights equally the interior portion of the object, which are non-discriminative and are unlikely to get highlighted as per classification task. On COB dataset, we can observe that our method can detect whole object despite the object being blended with background and in cluttery environments. Thanks for listening.